Section: Introduction. In this section, we discuss the impressive capabilities of language models built on the transformer architecture, particularly in natural language tasks. These models are trained to predict the next word in large text datasets, which helps them develop a strong understanding of language and generation. A key goal in creating models that can mimic human-like intelligence is enabling them to reason and plan in complex, unfamiliar situations. Recent studies have shown that the deeper layers of transformers contain valuable information for solving certain mathematical reasoning problems, but we still do not fully understand how these models achieve such reasoning abilities. Our work aims to enhance our understanding of how transformers reason through simple propositional logic problems. To illustrate, consider this problem. If A or B implies C, and D implies E, with A being true, B being false, and D being true, what is the truth value of C? A minimal proof would be, A is true. A or B implies C, therefore, C is true. Although this problem seems straightforward, it requires the model to perform several critical steps without explicitly thinking through the process. The model must first identify the relevant rule, then use the values of A and B to find the facts, and finally determine that A is true, is the relevant fact to use in its answer. We believe this problem is a good starting point to explore how a model understands and plans for solving more complex reasoning tasks, especially when the problem has ambiguities that are not easily resolved. To investigate how transformers tackle such problems, we conduct two types of experiments. The first involves shallow transformers trained solely on synthetic propositional logic problems, allowing for detailed analysis in a controlled environment. The second set of experiments uses a pre-trained large language model, Mistral 7B, where we apply activation patching to identify the necessary components for solving the reasoning problem. From our analyses, we find that small transformers trained on synthetic problems use specific routing embeddings to change how information flows in the deeper layers when addressing different types of reasoning problems. We also identify various reasoning pathways, noting that problems requiring logical operators typically engage more layers of the model. In the Mistral 7B experiments, we discover four types of attention heads with specialized roles: those that locate the queried rule, those that move the rule, those that process facts, and those that make decisions. We observe that the model follows a natural reasoning path from querying the relevant rule to identifying the relevant facts and making a decision. We define the scope of our analysis clearly. In the shallow transformer experiments, we focus on models that only include self-attention layers, layer normalization, positional encoding, embedding, and softmax parameters, as these already achieve perfect accuracy on the problem. In the Mistral 7B experiments, we concentrate on identifying the components essential for the model's reasoning circuit, rather than trying to uncover every component involved. Our work fits into the broader field of mechanistic interpretability, which seeks to understand the mechanisms behind the capabilities of large language models. We define a circuit as a collection of model components with information flow indicated by connections between them. Additionally, we relate our work to studies that evaluate the reasoning abilities of language models across various tasks, focusing on how transformers reason through logic problems that allow for detailed analysis. Finally, we note that there are few studies that provide a fine-grained analysis of how language models reason. Our research aims to fill this gap by examining both small transformers trained on synthetic problems and larger models trained on extensive datasets. We also utilize activation patching, a method that employs causal interventions to uncover the internal mechanisms that enable language models to perform specific tasks. This involves running the model on original and altered prompts to identify components that change the model's behavior. Section Summary. In this section, we explore how transformer models reason through simple propositional logic problems, aiming to understand the internal mechanisms that enable this reasoning. Our experiments reveal that small transformers utilize specific routing embeddings to manage information flow, while a pre-trained model, Mistral 7B, employs specialized attention heads to follow a reasoning pathway from querying rules to making decisions. Section: Data Model, a propositional logic problem. In this section, we describe the synthetic propositional logic problem that serves as the data model for our paper. Our problem is based on an implicit causal structure, which includes two separate chains, one with a logical operator at the end and another that is purely linear. We need the model to create a minimal reasoning chain that includes relevant facts, appropriate rule applications, and intermediate truth values to answer a truth value query. For example, using the causal graph, we can express the rules as follows. K implies D, D or E implies A, V implies E, T implies S, and P implies T. The facts are that K is true, P is true, and V is false. The query is A, and the answer is that K is true, leading to D being true, which in turn makes a true. Here, the query token A is the endpoint of the OR chain, and since any true input to an OR gate results in a being true, we only need to select one starting node from the OR chain, which is K in this case. To find the minimal proof and solution strategy, we must carefully analyze the rules, facts, and query. First, the query token helps us identify the chain needed to deduce its truth value. If we are querying the logical operator chain, we check the facts to determine the correct starting points for our reasoning. This step is not necessary for the linear chain. Finally, we invoke the rules to deduce the truth value of the query. The first answer token is crucial for the accuracy of our proof, as it requires us to process all context elements correctly due to the minimal proof requirement. In the next part, we examine how small transformers, similar to GPT-2, trained only on this logic problem, approach and solve it. We focus on two main questions: how the transformer processes the context and plans its answer before generating any tokens, particularly how it predicts the first token, and how it determines the truth value of the query at the end. We emphasize the first question because the first answer token reveals much about the transformer's mental processing of the context without relying on a chain of thought. We analyze decoder-only attention transformers that resemble GPT-2, training them exclusively on the synthetic logic problem. During training, we query the logical operator chain 80% of the time and the linear chain 20% of the time. We choose a three-layer, three-head transformer for our analysis, as it is the smallest model that can achieve 100% accuracy. The model generally follows a strategy to predict the first answer token. At the query position, the second layer's attention block sends a routing signal to the third layer, indicating whether the linear chain is being queried. If the query is for the linear chain, the third attention block focuses almost entirely on the query position, as the correct answer is already present. However, if the logical operator chain is queried, the third layer constructs a partial answer, which it then refines. The query token is vital as it determines the chain type and influences the third attention block's behavior. The routing direction in the embedding generated by the second layer indicates whether the linear or logical operator chain is being queried. A positive routing signal leads the third layer to focus on the query position, while a negative signal shifts attention to the rules and facts, allowing the model to output the correct first token for the logical operator chain. We provide evidence for this mechanism, showing that the second layer's output varies based on the queried chain type. When the linear chain is queried, the third layer focuses heavily on the query position, while it shifts attention to the rules and facts for the logical operator chain. To further validate our findings, we compute the routing signal and test its influence on the model's reasoning. By manipulating the routing signal, we can switch the model's reasoning mode between linear and logical operator chains, confirming the existence and role of the routing signal in determining attention patterns and overall output. Section Summary. In this section, we describe a synthetic propositional logic problem that utilizes an implicit causal structure with two chains, one involving logical operators and the other being linear, to generate minimal reasoning chains for truth-value queries. We analyze how small transformer models, trained on this logic problem, process context and determine the first answer token, revealing that the query token significantly influences the model's attention behavior based on whether a linear or logical operator chain is being queried. Section Answer for the linear chain. In this section, we analyze the response for the linear chain. We observe that when the query pertains to the linear chain, the third layer primarily functions as a simple message passer, transferring information from the layer 2 residual stream at the query position to the answer position. A key question arises. Does the input to the third layer actually hold the information needed to identify the first token of the answer, which is the starting node of the linear chain? The answer is affirmative. For our second piece of evidence, we utilize a linear classifier trained with the same input as the third attention block at the query position, targeting the start of the linear chain. We generate 5,000 training samples specifically for the linear chain and achieve a test accuracy exceeding 97% on these samples, confirming that layer 2 already contains the answer at the query position. Next, we address the log-op chain, where we find that the first two layers provide a partial answer, and the third layer refines this information. To accurately predict the starting node of the log-op chain, the model follows a specific strategy. The first two layers encode the log-op but only deliver a partial answer. We find that when the log-op is an AND gate, layers 1 and 2 typically pass nodes with a false assignment to layer 3. Conversely, for an OR gate, they pass nodes with a true assignment. The third layer then combines information from the two starting nodes of the log-op chain and the layer 2 residual stream at the answer position to produce the correct answer. We will provide further evidence for these claims in the appendix. Our argument relies on linear probing and activation patching, demonstrating that while we cannot linearly decode the answer from the layer 2 residual stream, the predictor's answer exhibits a specific structure resembling a partial answer. This residual stream also contains valuable answer-specific information, such as the context of the log-op. Additionally, through activation patching, we confirm that the layer 2 residual stream significantly influences the correct answer, reinforcing our claim of a partial answer in layer 2 leading to refinement in layer 3. Now, we turn our attention to how the pre-trained LLM, Mistral 7 BV0.1, addresses this reasoning challenge. We selected this model because it is one of the smallest available that achieves over 70% accuracy on a simplified version of our problem. Our focus remains on how the model deduces the first answer token without any chain of thought, COT. This is crucial since determining the first answer token requires the model to effectively process all contextual information without relying on COT. We outline the main characteristics of the reasoning circuit within the model for this task. Overall, we note several interesting features of the LLM's reasoning circuit. Compared to the attention blocks, the multi-layer perceptrons, MLPs, are less critical for accurate predictions. A limited number of attention heads are central to the reasoning circuit. Some heads locate the queried rule using the query token and store this information at the query position, while others move the query and the queried rule information to the designated position. Additional heads identify relevant facts and transfer this information, and finally, one head makes the decision on which token to output based on the aggregated information. In our Mistral 7B experiments, we provide input samples with specific properties. We present the model with 6 randomly chosen in-context examples before requesting an answer. The problem is structured to involve only one rule with an OR gate and one linear chain rule, with the answer consistently being true. Specifically, the truth values of the two premise nodes in the OR chain always include one false and one true. We designed the first point to ensure fairness to the LLM, which was not trained on our specific logic problem. The last 2 points are intended to guarantee that the first answer token is unique, enhancing the analysis's tractability. Importantly, these restrictions do not diminish the core challenge. The LLM must still process all contextual information without COT to determine the correct first token. Section Summary. In this section, we demonstrate that for the linear chain, the third layer effectively relays information from the second layer to determine the starting node of the answer, achieving over 97% accuracy in our tests. For the log-op chain, we find that the first 2 layers provide a partial answer, which is refined in the third layer, with specific attention heads playing crucial roles in processing and decision-making within the reasoning circuit of the Mistral 7B model. Section: Causal Mediation Analysis. In this section, we provide evidence using a well-known method in mechanistic interpretability called causal mediation analysis. Our approach is as follows. We focus on the activations of specific components of the large language model, LLM, related to a particular task. For instance, we want to understand how attention heads contribute to processing query information for inference. We denote the activation of head H in layer L at token position T as A_L, H, T, X. We start by creating two sets of prompts that are slightly different. In our example, we define two sample sets, D_orig and D_alt, where the context is the same, but in D_orig, query is for the log op chain, while in D_alt, query is for the linear chain. We also identify the correct targets for each set. We run the LLM on both sets, recording the attention head activations and the model's logits. We calculate the difference in logits, delta_orig, n, which should be large for a high accuracy model, indicating it can distinguish between the two query types. Next, we perform interventions by running the model on D_orig but replacing the original activation A_L, H, T, D_orig, with the altered A_L, H, T, D_alt. We denote the logits from this modified run as logit_to_alt, L, H, T, D_orig. We then compute the intervened logit difference, delta_orig_alt, n, L, H, T, and average these differences over all samples for each layer, head, and token position. This helps us identify which components are crucial for processing query information. A significant positive delta_orig_alt, n, L, T, indicates that the activation plays an important role in shifting the model's understanding from one query type to another. We also note that due to the symmetry in our example, we can perform the reverse interventions as well. In the next part, we analyze the reasoning circuit of Mistral 7B, presenting our findings from broader to more detailed aspects, which enhances the clarity of our discovery process. We reserve more complex experimental results for the appendix. We begin our analysis with query patching to identify the key attention heads involved in context processing and inference. Query patching is vital for discovering the reasoning circuit because the query token is essential for starting the reasoning process. Without it, the rules and facts are ineffective. With it, the model can identify relevant information to generate answers. Since the only difference between our prompt pairs is the query token, a significant change in the model's logits after intervention indicates that the component is crucial to the reasoning circuit. We present higher-level intervention results, where we modify residual streams, attention blocks, and MLPs. Our findings show a clear transition in query processing between layers 12 and 13. We observe that only a few attention blocks in layers 9, 12, 13, 14, 16, and 19 are significant for altering the model's beliefs. The MLPs contribute minimally, except for MLP0, which functions more as a nonlinear token embedding rather than a complex processing unit. We focus our analysis on the attention heads and will explore the role of MLPs in future work. In our attention head interventions, we identify a small number of attention blocks that are crucial for the task. However, we still have too many components to analyze in detail, so we conduct finer-grained experiments on the attention heads. Our results reveal that only a few attention heads are central to altering the model's beliefs. Specifically, we find that heads 12, 9, 13, 11, 14, 24, 2, 6, 16, 0, 12, 14, 17, 25, and 19, 8, 9, 16 show high intervened logit differences. We also consider the grouped query attention used by Mistral 7B, which complicates the analysis since patching one head may not significantly change the logit difference if other heads in the same group perform similar functions. Therefore, we conduct a coarser experiment that patches all heads sharing the same key and value activations, revealing that heads in the group 9, 24 to 27 also exhibit high intervened logit differences. Section Summary. In this section, we employ causal mediation analysis to investigate the role of specific attention heads in a language model's reasoning process, particularly how they influence the model's interpretation of query information. Our findings highlight a small subset of attention heads that significantly alter the model's beliefs during inference, emphasizing their critical role in the reasoning circuit. Section: Finer examinations of the attention heads. In this section, we examine the significance of the attention heads identified earlier. We focus on altering the query in the prompt pairs and analyze the subcomponents of each attention head, specifically their value, key, and query. Our findings reveal four main types of attention heads. First, we discuss the queried rule locating head. For attention head 12, 9, we observe a significant difference in its query activation, indicating that its query and attention patterns depend on the query and influence the model's beliefs. Notably, this head maintains an average attention weight above 90% at the conclusion variable of the queried rule, meaning it effectively identifies and retains the rule's information at the query position. Next, we look at the queried rule mover head. Attention head 13, 11 shows a large difference in its value activations, while its query and key activations do not exhibit the same pattern. This suggests that its attention pattern consistently acts on both original and altered prompts, with only the value information being sensitive to the query. In the relevant context, this head allocates over 50% of its attention to the query position, with its attention weight at query being about 10 times greater than the next highest. We then analyze the fact processing heads. Attention heads 16, 12, 14 demonstrate significant differences in their query activations, directing over 56% and 70% of their attention, respectively, to the fact section of the context. Lastly, we consider the decision head. Attention head 19, 8 also shows large differences in its query activations. Its attention pattern indicates it functions as a decision head, consistently focusing on the correct starting node of the queried rule and the appropriate variable in the fact section when the model is correct. These two token positions account for more than 60% of its total attention in the relevant context. Due to space constraints, we will provide more detailed experiments and insights in the appendix, including a closer look at the attention patterns of these head families and additional validation for the queried rule locating heads, fact processing heads, and decision heads.